Let's dig into our favorite oscillator, the simple harmonic oscillator. What a wonderful thing it is. And the book unabashedly puts in the abbreviation simple harmonic oscillator. Interesting acronym there. So let's think about that. Lots of things do this approximately. Many things oscillate, and usually those oscillations are pretty close to simple harmonic oscillator. That just means you can use sine waves to describe it. You don't need extra things on there. You can get it, therefore, from contemplating motion around a circle. Just take the cosine, you get the x component, or take the sine, you get the y component, with time. So if you think of a wheel turning at a constant angular velocity, that's an example of a simple harmonic oscillator. So you can build these things at slow-mo, but you can also see them in action with strings and pendulum situations, masses on a spring, other things as well. So let's suppose we had a guitar and we plucked that string back. So let's make some graphs. Position versus time. So we'll start off up here. Then we'll let the string go, and it will respond. It will go back toward the neutral position. So that middle line means the relaxed position. Now, when we started, that position up there, that the velocity was 0. That was all potential energy. It was all spring potential energy and no kinetic. So the velocity is 0 at the start. The acceleration is negative at that point. It's trying to get that string back to the center. And so the acceleration is negative. Now at the neutral position, it's the opposite for velocity. The velocity is downward for one thing, and it's all kinetic, and there's no spring potential energy right there. So the velocity is down here. In fact, it's another sine wave. And the acceleration had been at maximum, but it's coming up to when x is 0, f is 0, and so f equal ma, so a is 0 as well. So acceleration goes to 0 at that point. So okay, got these weird little arcs going on, but if you continue, they all look like the same wave except shifted from each other. So that spring or string will pass through the center point and then slow down until it reaches the negative maximum right there. At that point, the velocity is going to be 0 again. The acceleration, though, you got maximum force and it's positive, so your acceleration is going to be a maximum right there. And we can continue. So this goes through another cycle, and then this goes through another cycle as well. And these are all of the same shape. So those are all sine waves where we've stuck in our sine formula somewhere. We've got some kind of sine or cosine with a time variance on it. So if we got angular velocity of radians per second times seconds in here, this is exactly what we've got for those guys, but shifted. So, and also different units. So all those waves are going to be sine waves. All right, so that's that's a way of looking at the simple harmonic oscillator. There's so many videos on YouTube about this that do a better job than what my lips are doing. And then the punchline here is that for all these simple harmonic oscillators with a force law that can be written as force minus kx, for all those cases, the period of oscillation t is a 2 pi times square root of m over k. And then the frequency being 1 over the period, like that, is 1 over 2 pi. And then you just flip that thing, k over m. So forth. So these are for our simple harmonic oscillator. And it's kind of cool because that transfers to a lot of different physical situations. Pretty much everything that vibrates will obey this almost perfectly.